So dear students, in today's class, we will continue with our previous discussion on filters. As I told you in the previous class, filter is an integral part of your network analysis and synthesis subject. In fact, filter is an integral part of any electronic or electrical system which exist. Okay, and it is very important also to understand the concept of filters. So basic concept of filter, we already know that the main purpose of filter is to filter out certain frequencies, or in other words you can say that filters pass certain frequencies or filters reject certain frequencies. Okay, so that way your filters assume importance in every circuit that we have studied or we will be studying in other subjects also. Okay, so as I told you in the previous class also that there are different types of filters, and the most common category of filter is active filters and passive filters. And as we discussed previously, uh, in previous class also and in today's class also, our main emphasis is on the passive filters. Okay, so so your constant K filter will be a kind of passive filter, as we have talked about in the previous lecture. Okay, so in the last class we had also seen the concept of constant K filter. We had seen the design of constant K low pass filter. So hurriedly, within 4 or 5 minutes I will revise the content of previous lecture so that you are able to connect with today's lecture. And let me tell you one very important thing here. Though we have in mind that okay, filters are some electric circuits, and there will be certain electrical components like resistance, inductance and capacitance, and when we study about filter, you will come across complete mathematics. So students, I have told you this thing earlier also. Basically mathematics is helping us to understand the concept of electrical system, and filter is no exception to that. So we are trying to mathematically model the concept of filters, and then we are trying to understand the working of those filter. So that way, without correlating mathematics with your actual systems, we will not be able to understand completely. So that way you should pay full attention to the working of filter with the help of mathematical expression. So keep this thing in mind. In fact, in whatever lectures we have covered so far related to various topics in network analysis and synthesis, those every topic had a put of mathematics in it, starting from topic 1 till today's is your 32nd lecture. So mathematics help us in getting the thing simplified and understand that thing logically. So we will justify things mathematically with the help of mathematical expressions, and then we will physically realize those filters. So that is the way we try to understand engineering circuits. Okay, so I hope the genesis of the lecture that we our topic we are going to cover today, it is clear in your mind. So let me move forward. So as I just told you that we are going to cover passive filter, and your passive filters, these contain your impedances in the form of your inductor and capacitor arranged fine, either in series or in parallel. And we will study two type of circuit sections, you can say T sections or pi sections. uh, I have covered this thing in detail in the previous class. So in T section, your circuit will look like a T, like this. So this circuit looks like a T section. Okay, and we have seen its derivation also in the previous class. One circuit has been drawn for you in this slide. This looks like pi. Okay, so we call it as pi section. Fine. So we'll have inductors and capacitors arranged in series or parallel in case of your passive filters. Now another important thing related to filter is the cutoff frequency. So that is quite understandable, and we have talked about this thing in detail in the previous class. So in every filter there will be a cutoff frequency. So cutoff frequency distinguishes your pass band and your stop band. Okay, so it demarcates your pass band and stop band. The meaning of pass band, stop band is already clear to you. Then another very important design parameter for a filter was characteristic impedance, that is your Z naught. I had explained about characteristic impedance in the previous class. We all have studied two-port network parameters, and there we studied about one important parameter, that is your driving point impedance. Okay, so this characteristic impedance is a kind of driving point impedance only for the filter. Okay, and if your driving point impedance or input impedance becomes equal to the load impedance or the impedance of the circuit to which your filter is connected, then maximum power transfer takes place or minimum reflection losses take place. So that way characteristic impedance is very, very important. See, students, here try to understand the main aim of this lecture or this topic filter in this subject is to understand how to design filter. See, we are not simply studying that what is low pass filter, what is high pass filter. That is simple concept. So like if some requirement is given to you that, okay, I want a filter with certain cutoff frequency, with certain characteristic impedance, can you design a filter for me? And designing of a filter means deciding the values of the components, that which value for the inductor you should take, which value for the capacitor you should take, that will satisfy the requirement of either the customer or any other project where that filter will be used. So here our main objective is to understand the designing of the filter. That is actually the engineer's job. Okay, so whatever requirement is given to you, we design our circuit according to that requirement. Keep this thing in mind, please. Let us now move forward. So then another thing is, what are the different pass band characteristics? Okay, so when we say pass band and stop band, in pass band the attenuation is minimum, and in case of stop band the attenuation is maximum. So you have a new term that we call attenuation. Okay, so we will also represent this attenuation mathematically. In fact, we have talked about this attenuation in the previous class also, and I will advise you people, though I covered everything in the previous lecture, yesterday's lecture, uh, when you listen to today's lecture, after that you again go through the video of previous lecture. That is very, very important to develop complete understanding of the topic. Okay, so after this we have talked about constant K filter. We also call constant K filter as prototype filter. This is one and the same thing. And why are we calling it as constant K filter? Because Z1 into Z2 is equal to some constant K. And I hope you have recalled what is Z1 and what is Z2. Let me tell you again. Z1 is your series arm impedance of your filter circuit, and Z2 is the parallel arm impedance of the filter circuit. Okay, total uh, impedance of the parallel arms of the circuit. So if you multiply those, it will give you some constant value. That's why it is called as constant K filter. So this is a feature of constant K filter, that when you multiply the complete impedance of the series arm as well as the parallel arm, you will get a constant, and that constant we represent in the form of R naught square, and we call this R naught as a design impedance R naught. Okay, so this R naught is design impedance and Z naught is characteristic impedance. Mind this thing, these are different things. R naught is a design parameter which is equal to under root K. You can see here. and Z naught is your characteristic impedance. Fine. So this R naught is a real number and it is independent of the frequency. It does not depend on the frequency and it is a constant number. Okay. So this is what we had seen in the previous class. As I told you that how basically we analyze prototype filter section. So here we are not talking about whether it is low pass filter or high pass filter. If we have a constant K filter or a prototype filter, what we need to find out, we need to find out one thing is characteristic impedance. Okay, so if we have T section, okay, see this is a T section. So this is the T section and the T section is having load Z naught, means we are assuming that our load impedance is equal to the characteristic impedance so that maximum power transfer takes place. Okay, so we are finding out the driving point impedance or the characteristic impedance of the T section, okay, which has load Z naught. So we had seen its derivation in the previous class, and if you derive this you will come out with this expression. Z naught is characteristic impedance of T section, and this is the formula under the root Z1 square by 4 plus Z1 into Z2. And this is how we have obtained it. Here you can see that we have Z1 by 2. It is in series with parallel combination of Z2 and this Z1 by 2 plus Z0. See. So if you carefully look at this, you will be able to understand how actually we have derived this. So this is your characteristic impedance of the T section, which we saw in detail in the previous class. Now, as I told you that I introduced one term to you, that is your attenuation. So in case of your pass band attenuation, ideally in case of pass band, your attenuation should be 0. Okay, so if we are passing anything, it means nothing will be attenuated. Whatever we are giving at the input, this will be passed, and that means your attenuation should be 0 in case of pass band. Okay, so this attenuation is defined with the help of a parameter that we call as gamma. So this gamma is known as propagation constant. Okay, this gamma tells us that how effectively your circuit will be able to pass your signal. That's okay. So that passing the signal means propagation. Okay, so if your signal is properly propagated without any loss, we'll say attenuation 0 and it is in the pass band. And if the propagation is stopped, it is not allowed to pass through, then we can say that maximum attenuation is taking place and there is a stop band for that. Okay, so I had explained the derivation of this propagation constant in detail in the previous class, and I have reproduced that derivation here for you. So this circuit has been used to find out the value of gamma. You can go through my previous video and you will be able to understand its derivation. Okay, so finally what we arrive at this expression for your propagation constant. Okay, so we define propagation constant like this: cos hyperbolic of gamma is equal to 1 plus Z1 by 2 Z2. So what we have done, we have expressed at propagation constant in the form of again Z1 and Z2. And if you see in the previous slide, we have also expressed the characteristic impedance in the form of Z1 and Z2. Okay, so we further elaborate this propagation constant gamma. This is equal to alpha plus j beta, means gamma is a complex number. So where real part is alpha and your beta is the imaginary part. Okay. Now this alpha is known as attenuation constant. Very, very important thing. So alpha is known as attenuation constant and beta is known as phase shift constant. Phase shift constant. Okay, I hope you are able to recall what I told in the previous class. Okay, so alpha is your attenuation constant and beta is your phase shift constant. Okay, so obviously, as I told you that in case of pass band, your attenuation is 0. What does it mean? That in case of pass band, the value of alpha will be 0. Okay, so if alpha is 0, it means gamma will be an imaginary number. Okay, in case of your pass band. This you need to remember, and you correlate. See what I am doing? I am correlating mathematics with the concept of the filter. Please try to understand. So we have correlated our pass band and stop band with the help of attenuation constant or propagation constant. Another thing, we have talked about characteristic impedance. This you also need to remember, that for the case of pass band, your characteristic impedance value will be real. Z0 is real for pass band, and this I told you that attenuation alpha is 0. This is for pass band P. Okay, whereas in case of stop band, Z0 will be imaginary. This is another characteristic or important point to note, that in case of stop band, Z0 will be imaginary, that is characteristic impedance will be imaginary, and in case of your pass band, your characteristic impedance will be real. Okay, and obviously in case of stop band, your attenuation cannot be 0, it will be some constant. Okay, obviously alpha will be having some value, beta will definitely exist. Okay, so this was the concept that we had talked about in the previous class. I hope you are able to recall. Next, so by following the analysis of the prototype filter, generalized analysis, as we have seen in the previous 2 slides, we can now move to design of low pass filter. Okay, so there we had generalized expression in the form of Z1 and Z2. We had not uh, defined that what will be Z1, what will be Z2. See, your characteristic impedance is in the form of Z1, Z2. Your propagation constant is also in the form of Z1, Z2. Now the value of Z1 and Z2 will be different if your filter is low pass filter, if your filter is high pass filter, if your filter is band pass filter, if your filter is band stop filter. Okay, so whatever filter you take, if you take low pass filter, you substitute the value of Z1, Z2 corresponding to that. If you consider high pass filter, you substitute the value of Z1, Z2. So job is highly simplified. So dear students, you have to simply follow or understand these 2 slides completely, along with their derivation, that what is the concept of characteristic impedance and what is the concept of your propagation constant. So if you understand the expression of these, you will be able to follow these expressions very easily in every type of filter. Okay, let me show you how. See, so what we are considering low pass filter. This also I had covered in the previous class. So here on the left hand side, I have shown the circuit of the low pass filter. Okay, I explained the working of low pass filter in the previous class, that how does this circuit and this circuit act as a low pass filter. This has already been explained yesterday. Okay, so I'm assuming that you remember this thing completely fine. So what we are supposed to have here, see, what is Z1? First, let us see here. Your Z1 is, I told you, that complete impedance of the series arm. Your complete impedance of series arm will be J omega L. Both are in series. Okay, your complete impedance of the shunt arm or the parallel arm will be 1 by J omega C, or minus J by omega C. Okay, so this is our Z1 and this is our Z2. That's it. We simply need to know this thing, that for low pass filter, Z1 is this one and Z2 is this one. Okay, whether it is T section or pi section, that is another thing. That is just the way we are representing those components or distributing those components. Otherwise, determining the value of L and C for low pass filter, it will be the same whether it is for T section or pi section. Once we have determined L and C, we will distribute according to the circuit that we have shown. If we are following T section, then we will distribute the value of inductance in the form of 2 inductors, and capacitor will be a single capacitor. If you want to use those values of L and C as pi section, In that case, you will take single inductor of that value and you will distribute the value of capacitance as two capacitors. Okay, so that is another thing. Now, since we have seen Z1 and Z2, first let us see whether it is following the main definition of your prototype filter or constant K filter. So what we do, we obtain Z1 into Z2, and this Z1 and Z2 should be a constant. So if we do that, we get a value L by C, which is nothing but a real number and a constant value, that is K. And we have represented that K as equal to R naught square, where R naught is your design impedance, as we have already seen. Okay, so from this expression, what do we get? We get R naught is equal to under root L by C. Okay, so if you are being given L and C, you can easily determine the value of design impedance, that is R naught. Now next, this is what we had seen in the previous class, that your cutoff frequency or cutoff will take place when this omega square LC by 4 equal to 1. So I have not gone in the derivation of this expression in today's class, but its derivation has been completely covered in the previous class. So if you are not able to recall, I'll advise that you again go through the video and you find out. So if you solve this for omega C, you get this one. Okay, so your cutoff frequency for your low pass filter, which is of the type prototype or constant K, you get omega C is equal to 2 by under root LC, which gives us FC equal to this. Okay, so what we have got, we have expressed our design impedance in the form of L and C. We have expressed our cutoff frequency in the form of L and C. Okay, and then what we are doing by using these two expressions, we are trying to find out the reverse thing. Like if you are given R naught, if you are given FC, then can you find out L? This is what we are doing. We are expressing now L in the form of design impedance and cutoff frequency. We are expressing capacitor in the form of your design impedance and your cutoff frequency. Okay, this is what I was talking about. You will be given in a numerical or a problem, you will be asked that, okay, design a filter with this much design impedance and this much cutoff frequency. So and you have to design, say, low pass filter. Then what you will do, you will simply substitute the value of R naught, you will substitute the value of FC, apply this formula, find out L. Similarly, by applying this formula, you will apply C, find out C. So once you have found L and C, you will substitute the value of L and C either in T section or pi section, whatever is the desired one, and you will give that filter to the person who has asked for the solution of his or her problem. Okay, I hope that this thing is clear to everybody. So students, now we move to our next discussion, and we will now talk about the analysis of prototype high pass filter. So till now we had talked about low pass filter, and now the discussion will be on the high pass filter. So if you look at the circuit diagram of high pass filter carefully, then you will see here that in case of low pass filter, we had inductor here, we also had another inductor here, and we had capacitor here. Whereas in case of high pass filter, wherever inductor was there, it has been replaced with a capacitor. Same is the case in your pi section. In case of low pass filter, we had an inductor here, and in case of again low pass filter, we had two capacitors, so which have now been replaced by the inductors. So this is the simple methodology with the help of which you can memorize that if you know the circuit of low pass filter T configuration as well as pi configuration, you can easily make out the configuration for high pass filter as well. This is one point. Another point is that you can easily see the working of high pass filter, as I explained yesterday also, that this is your capacitance, and you know what will be the reactance of the capacitor for low frequency, for high frequency. If you apply this concept, you will be able to easily understand the working of high pass filter. Okay, so here again we will do the same thing. In high pass filter, what is the value of Z1? The value of Z1 is 1 by j omega c, because we have in series arm we have capacitors. So total capacitance is 1 by j omega c, which becomes minus j by omega c. Okay. Similarly, your shunt impedance Z2, it is nothing but j omega L. So in a way, you can say that things have interchanged in case of high pass filter. Whatever was Z1 in case of low pass filter, it has become Z2. And whatever was Z2 in low pass filter, it has come as Z1 in case of your high pass filter. Okay. So I hope you have understood. Again, if we check whether it follows the principle of constant K filter or not, we multiply Z1, Z2, and we get a constant value L by C, which is nothing but R naught square. So the multiplication of Z1, Z2 is obviously same because the values are same. So Z1 into Z2 is constant value L by C, which is equal to R naught square. Okay. So this generalized expression we had seen for while analyzing a prototype filter. Uh, this is the characteristic impedance for T section, irrespective of whether your filter is a low pass or high pass. Now what we will do here, we will substitute Z1 of high pass filter. We will substitute Z2 of again high pass filter. So if we do that, you get this expression. So I'll advise you that you do this analysis on your own by substituting the value of Z1, then squaring it, then multiplying Z1, Z2, then you will be able to clearly understand. Otherwise, if you are a fast learner, you can find it out just by looking at the expression in this slide only. So this is nothing but your Z1 square by 4, and your Z1, Z2 is nothing but L by C. This is L by C. So what we have now done, see, if you remember the cutoff frequency, uh, see what we have done, we have taken under root of L by C common outside this. So what we are left with 1 minus 1 by 4 omega square CL. Okay. And what is under root L by C? Under root L by C is nothing but R naught. So we have represented this by R naught, and we get R naught under the root 1 minus 1 by 4 omega square LC. So this is your characteristic impedance of a high pass filter having T configuration. Okay. See, this was general expression, which will be same for every type of filter. But once you substitute the value of Z1 and Z2 for low pass filter, this will become the characteristic impedance of low pass. If you substitute the value of Z1, Z2 from high pass filter, this will become the characteristic impedance of high pass filter. See, now the characteristic impedance of the T section of high pass filter is R naught under the root 1 minus 1 by 4 omega square LC. This you have to memorize. Okay. And now if we move forward, and as I told you that in case of pass band, our characteristic impedance, it should be real. Okay. So this is our characteristic impedance. When it will be real, this will be real when the value inside this under the root, it should be positive. Because if you have negative value under the root, then it will give us imaginary value. I hope you already know that if we have minus of x, this will give us some imaginary value, isn't it? So if you have plus of x in the under root, then you will get some real value. Correct? So here we have 1 minus. It means for this to be real, this value 1 by 4 omega square LC, it should be less than 1. So if it should be less than 1, that will give us that 4 of omega square LC, it should be greater than 1. I hope you understand. If I say that 1 by x should be less than 1, that means your x should be greater than 1. I hope you have followed this. So same logic applies here. So for Z naught to be real, that is your pass band, your 4 omega square LC, it should be greater than 1. For attenuation band, or you can say stop band, your Z naught T should be imaginary, and it will be imaginary when this value will be greater than 1. If it is greater than 1, then for omega square LC will be less than 1. I hope you have followed that. So what do we have? For this value greater than 1, pass band. For this value less than 1, stop band or attenuation band. And what will happen when this value is equal to 1? That means this is nothing but our cutoff frequency. Remember how I defined cutoff frequency. Cutoff frequency was the frequency which demarcates pass band and stop band, or pass band or the attenuation band. So what is demarcating here? 1. Okay, so 1 value for value of omega c. So if you solve this, you find out the cutoff frequency. So this is the cutoff frequency which is demarcating the pass band and the attenuation band. So for prototype high pass filter, the cutoff frequency will be 1 by 4 pi under root LC. And you see this cutoff frequency and this characteristic impedance is different from what we have seen in the low pass filter. Let me show you. See here that here your cutoff frequency was 1 by pi under root LC. Whereas in case of high pass prototype filter, your cutoff frequency is 1 by 4 pi under root LC. There is a difference. So this is your cutoff frequency and this is your characteristic impedance for T section. And here again, you can substitute the value of FC in this expression and you get this. Z naught T equal to R naught under the root 1 minus FC upon F. So this characteristic impedance has now been expressed in the form of cutoff frequency, and F is the general frequency. So here also you can apply this concept of real and imaginary, and you will find that you can here prove mathematically that this filter is high pass filter. How? See, for F greater than FC, if F is greater than FC and F is in the denominator, then this value will be less than 1. If it is less than 1, Z naught will be real. And if Z naught is real, it means pass band. So it means for all the frequencies F greater than FC, your filter is having positive characteristic impedance, means it is the pass band. It means it is passing the high frequencies. Whereas if F is less than FC, means lower than cutoff frequency, your Z naught T will be imaginary, means the stop band. I hope now you are able to correlate your characteristic impedance, your cutoff frequency with your concepts that we have developed so far. So this was your high pass filter. Now we find out the value of characteristic impedance for pi section. In the last slide, we have obtained the characteristic impedance of the T section. So for pi section, there is one very simple formula from your two-port network theory, that if we are aware of characteristic impedance of T section, we can easily find out the characteristic impedance of the pi section. That is Z naught pi is equal to R naught square by Z naught T. So we already know R naught square. We have already obtained Z naught T in the previous slide. So if you substitute that, this is what do we get. And if you further simplify, this is what do you get. R naught by under the root 1 minus FC upon F square. This is your characteristic impedance of the pi section. So I think now you have got the catch that you need not memorize both Z naught T and Z naught pi. If you know the value of Z naught T, you can easily find out the value of Z naught pi by applying this simple formula. Okay. So and rest of the things, these are the same as we have seen in the previous slide regarding your pass band and your attenuation band. Okay, so this was your pi section. Now let us see the propagation constant as we saw in the generalized form. So here, as I told you and I showed you in the previous slide, that your propagation constant gamma is expressed in the general form like this, where it is your cos hyperbolic gamma equal to 1 plus Z1 by 2 Z2. So as I told you, for high pass filter, you know the value of Z1, you know the value of Z2. So let us substitute. So our Z1 is nothing but the capacitor. So we have substituted 1 by j omega c. This is our inductor. So we have substitute the value of Z2 here. Okay. So if you solve that, what do we get? We get this one. Cos hyperbolic of gamma is equal to 1 minus 1 by 2 omega square LC. And gamma, as I told you, gamma is equal to nothing but alpha plus J beta. And now if you apply trigonometric theorem here, you know cos hyperbolic alpha plus J beta can be written like this. If you don't know, you can refer to your mathematics book. So this is cos hyperbolic alpha cos beta plus J sine hyperbolic alpha sine beta. Okay. So you can express this again in this form here like this. Okay. And see, this is an imaginary number, sorry, not imaginary, complex number of the form, you can say sum a plus j beta, sum a plus j b. This is complex number. Whereas on the right hand side, we have only the real value. There is no, j component or no imaginary value. So what does it mean? That this j part is 0. So it means sine hyperbolic alpha sine beta, this comes out to be 0. And this real part, it is equal to this one. This is what we have shown here. Okay. And see, this analysis regarding obtaining the value of propagation constant, we have seen in great detail while discussing the analysis of prototype low pass filter. So same analysis will apply to the high pass filter as well. So that's why I'm not going into that great detail as I went through in the previous class. So you can apply that detail here to obtain the final expression. So as I told you that for pass band, the attenuation constant, that is alpha, it is 0, means there is no attenuation. Okay. So what will happen? See here, I'm saying that for pass band, alpha will be 0. For alpha 0, cos hyperbolic 0 will be 1. So what we will be left with? Cos beta is equal to 1 minus 1 by 2 twice of omega square LC when alpha is 0. So from here, you can find out the value of beta, and this comes out to be like this. So beta is nothing but the phase shift constant. Okay. So for propagation constant gamma, we need to determine two things. One is alpha and another is beta. Okay. So beta has been determined from the pass band because alpha will be 0. Okay. And for the attenuation band, okay, so for the attenuation band, we can utilize this one. For attenuation, alpha cannot be 0. Since multiplication of these two is 0 and this cannot be 0, it means what is beta? Beta is nothing but some n pi. And we know that sine n pi is 0. Okay. So that thing has been utilized here. So for attenuation band, we have beta equal to n pi, and we take value of n equal to 1. So that's why we have utilized here beta equal to pi. So if we use beta equal to pi in this expression, so we know that cos of pi is -1. Okay. So then if you use this expression, you will be able to solve this. Okay. And finally, you are able to get the value of alpha from here. So I'll suggest you people to work out this on your own at your home. And in case of any difficulty, you can let me know in the next class. So I hope all of you are clear about this thing. So again, we have what we have derived. We have derived characteristic impedance of T section. We have derived characteristic impedance of pi section. We have derived propagation constant, and propagation constant has two things. One is alpha and another is beta. And then we have obtained the value of alpha and beta. After we have done this, what is the next step? We have to determine the design equations of the filter. We obtained the design equation of low pass filter. Now we will obtain the design equation of high pass filter. So let us see that. This is the design of your prototype high pass filter. Okay. So this we have already seen, Z1 into Z2 will be equal to R naught square, which is nothing but L by C, and which gives us R naught equal to under root L by C. And this is same as we had seen in the low pass filter. Similarly, uh, this is the cutoff frequency expression which demarcates your pass band and stop band. If you remember, this was the case here for omega square LC equal to 1. This gives us cutoff frequency. So same we have reproduced here. From here we obtain the cutoff frequency. This cutoff frequency is obviously different from the one obtained in the low pass filter. And now what we are doing, by utilizing these two, we are finding out the value of L and we are finding out the value of C in the form of your design impedance and your cutoff frequency. So same logic will apply that we had applied for the low pass filter. This you have to memorize, that for a prototype high pass filter, if you want to design a T configuration or pi configuration, then what will be the value of L or C if you know design impedance or the cutoff frequency. Okay, so I hope everybody is clear of this thing. So that was your design part of your prototype high pass filter, and I know that you must have understood the concept now completely about the designing of constant K filters, whether it is low pass or high pass. So if you understand these concepts completely, then discussing band pass filter and band stop filter will be very, very easy for us. So now we will see two very small numericals that will use these equations, and that will give you an idea that how to design filters uh, for the type constant K. So this is your numerical example 1. So here see, we have to design a constant K high pass filter. Okay, we have to design a pi section. What we are given? We are given cutoff frequency. We are given design impedance 600 ohm. We are not given what will be the value of L. We are not given what will be the value of C. This we have to design. Okay, so since it is K high pass filter, so let us see what are the values. For L it is R naught by 4 pi FC, and for C it is 1 by 4 pi R naught FC. See, what is C? 1 by 4 pi R naught FC. So what we have done, we have substituted the value of R naught. We have substituted the value of FC. FC was 4 kilohertz, and we obtained the value of C. Okay, so here now we need to determine the value of L. L is R naught by 4 pi FC. So here again we have substituted and we have determined the value of L. Very simple. This is so simple and numerical. Once you have understood the concept of designing, then applying those formula is kid's job. Okay, so once we have found the values of your L and C, now you can design either T section or pi section. It doesn't matter. So for pi section, if you remember, we had C here. So the value of C has come directly here. And then for pi section, we had the value 2L here. And we have obtained L. So for 2L, we need to use the value of 2 times this, that is cross 2, which will come out to be around 24. So this has come 23.874 similarly here. And you got a high pass filter of the type uh, constant K. Okay. Now let us see the next numerical. So here we have to design both T section and pi section. High pass filter obviously of the type constant K. We are given cutoff frequency. We are also given design impedance or nominal characteristic impedance R naught, this one. So again we apply the same formula. For L it is R naught by 4 pi FC. This is L we have got. This is C we have got by applying that formula. Now again, for let us take pi section first. For pi section what we had? We had C. So same value will come here. For pi section we had 2L here. So 2 times this. So that is around 19 millihenry that we have got. This is your pi section. Now you see for T section we have 2C. For 2C, This value of capacitor will be made twice and then written the value 0.054 microfarad. And here we have L only. So that's why this will not be made twice. So this L will come directly here. That's it. So just after understanding the concept, it is a very, very simple job to design the T section or pi section high pass filter. So students, with this, we have completed the designing and the analysis part of constant K low pass filter and constant K high pass filter. In the next class, we will talk about the band pass filter and the band stop filter of the type constant K. Okay.